Okay, hello everyone. My name's Mr. Pond. Before we get started completely, let me just give you this is just the link to my email. If you have any questions about the lecture, feel free to ask as we go along, and you can review these slides or send me an email if you have a specific question. Hopefully everyone can hear me. So yeah, this is geology today. It's pretty exciting. Weathering, erosion, deposition, and landscapes. And these words may be new, but we'll definitely go over all of them. So this is going to become very clear to you pretty soon. Weathering and erosion, these are two words that get confused with one another, but they're very different. As you can see here, weathering is the breakdown of rocks into smaller pieces. Erosion is where those pieces are moved in some way, and generally they're moved by these forces of nature, wind, gravity, glaciers. Sometimes they're moved by humans, which we'll talk a little bit about, or other organisms. Basically any way that these smaller rocks called sediments are moved. Weathering is just the process of breaking these things down so they can be moved. And then you have deposition. So when they're moved, where are they moved to? Where are they left? These rocks don't just disappear. They're deposited. So that's where this word comes from. They're deposited somewhere. And we're going to talk a lot more about that. And this definition that's given is the process whereby these sediments are released by their transporting agents. And that just means where they're dropped. It's very simple. Here's another thing. Weathering breaks down the rocks. Erosion moves the particles. Deposition drops the sediments. Particles, sediments, same thing. So like as we can see, these are all connected. This would be the first step. This would be the second step. And this would be the third step. Okay. So two primary types of weathering. So this is the breaking down of the rocks. You have chemical and you have physical. And it's important to note that these two things happen at the same time most of the time. But they are separated by definition. So physical weathering is the breakdown of rocks and minerals into smaller pieces. And the way it's different from chemical is that their composition stays the same. So they're broken into smaller pieces without a change in chemical composition. So you've probably seen some scenes like this just kind of wandering around. It's everywhere, and hopefully after this you'll pay more attention as you walk through the park or anywhere where there's rocks. You can see evidence of this weathering, and this is just how certain things break down rocks. And here we have ice, okay, and in the summertime maybe water gets into these cracks in the rock and then freezes. And if you know from chemistry class or from somewhere that ice expands when it freezes. So the water that's trapped in these rocks expands and kind of breaks these rocks into smaller pieces. The same kind of thing happens with these plants. They grow inside of these cracks and they start separating these rocks into smaller pieces. So you start off with just a block and then you can get ice. Abrasion is a really big physical weathering thing. We'll talk a lot more about that. Glaciers, which are big, gigantic, epic, massive, moving pieces of ice. Hopefully you've heard about them because they're amazing, but they have abrasion acting on the rocks in a very large scale. Another way, if you need another example of this wedging action, sometimes air is trapped within the rocks, and in a place where it's very cold at night and very hot during the day, sometimes the cold air is trapped in the rock, and as it heats up, it expands and can do the same thing as this, break up the break this up. So anywhere you can think of your own examples, anywhere where the something physical is breaking down these rocks, but it's not changing that. They're still the same chemical. So say this is made of silicon, which you may have learned in chemistry class. Silica is some rocks have large amounts of silica. They're not changing into silica carbonate or anything like that. They're still silica. They're just smaller pieces. Chemical weathering. So again, this is maybe happens at the same time as physical weathering. Maybe it's by itself, but it's very different from physical weathering. And the definition that's given is the breakdown of rocks and minerals into smaller pieces by chemical action. The rocks break down at the same time as it changes chemical composition. So what you end up with is going to be much different than what you started with. And very common, you'll see it all over the place, is oxidation. And basically it's whenever metals are combined with, they're left in open air for long periods of time, and water, which puts a solution onto the metal, which you don't really need to know, but just know that oxygen combines with the elements in the rock. So this could be made of iron, which is Fe, and it reacts, and the name of it is rust, and it's very common. You see this everywhere over time. Yeah, rust. Right, exactly. So you can see this all over the place, and it breaks down the metal, and it makes it weaker. Hydration. Sometimes water, which is H2O, can combine with earth materials and create silica dioxide or something like that, and dissolve away the earth by water. So that's, again, it's changing the chemical composition. Changes chemical composition. This is the main difference between physical and chemical weathering. So yeah, it's important to think of these things kind of similarly. They're acting together, chemical and physical weathering. Hydration. So say you have waves coming in and shaping the rock face. Okay, you could have hydration, which is water dissolving away the earth and combining with it and creating new materials, and changing chemical composition, and the waves bashing against the rock. That's physical weathering. So they act at the same time pretty regularly. Carbonation, you can kind of figure this out. Basically, carbon dioxide dissolves in water, and it creates this kind of corrosive material called carbonic acid. And this stuff, when it evaporates, it makes clouds that produce acid rain. And that can, when it comes into materials, falls on certain materials, it will erode them. So that's chemical weathering. If you say you have flood, which is physical weathering, and the flood comes upon a bunch of these rocks that are covered with carbonic acid, they're going to be washed away much more easily. So this would be another example of chemical and physical weathering at the same time. So what makes weathering easier? What makes this stuff easier? And this is a concept you may have heard of before, but say you start off with this block of rock, and then you have the ice kind of get in and expand and break this into pieces, and then this happens again and creates these little blocks. We know from geometry class, or if you don't know, this is just showing that 4 blocks have more surface area than 1 block. Okay, so even though this is the same mass, so these 4 blocks have the same, say this is 12 kilograms, okay, and these are each 3. Okay, the mass is the same between these two. 4 times 3 is 12. Then you still have more surface area. So this is just more access for things to contact the rock, and the more surface area, the increase in the rate of weathering. So this is really simple. If you kind of picture this in your head, you'll never get it wrong on a test. The more little blocks you have, the more small the particles are, the increased rate of weathering. So the smaller the particles, the highest rate of weathering. So if you have one gigantic boulder with no cracks in it at all, it's going to take the longest for that to become weathered or erode. Particle size, this is like I just said, larger particles weather slower and smaller particles weather at a faster rate. Just so you know, the smallest one, smallest kind of unit you're going to be working with is clay particles, and you can kind of put clay in your hands and feel it and see how small those particles are. Some particles that are smaller can dissolve in water, but generally you want to think about clay as the smallest kind of particle. So it's got the highest rate of weathering. Chemical composition. So is it a hard rock? Is it a soft rock? What's the density of the rock? If it's really hard, then it's usually much stronger and it takes longer to weather. So resistant rocks. This should all be kind of intuitive, but maybe this slide kind of helps me think about it, and hopefully it will help you. Again, this is a great slide to kind of reference. Maybe you want to copy and paste it and save it because it's got a lot of information just on this one page here. But let's continue. Chemical composition, I just did that. And climate, this is huge. If you're in a warm, moist climate, kind of like Bangkok, then you have a lot of weathering. The water and the heat that's around will increase the chemical reactions. These reactions do well when it's warmer and when it's when there's more water. This is a really important factor. Like I said before, climates where there's a huge increase or decrease in temperature between day and nighttime, it's very useful for weathering. It's easier for rocks to become weathered in climates like that. Okay, so this is kind of a blurry picture, but I think it gets the point across. We have these different horizons of the soil. So this is as things become eroded or weathered and then eroded, and they're deposited. They kind of are in these layers. This is the soil profile. Okay, and we can see evidence of this kind of layering if we just kind of dig down. And this is really good if you ever need to dig a really deep hole with one of your friends. You always want to dig first, because if you dig second, you're going to be into this like horrible bouldery area. You're just going to be hitting rocks every 5 seconds, and it's going to be really agonizing. So just be like, hey, I'll dig first, and then you get rid of this really light soil, and this stuff's easy to dig, and then right when you get to like here, you go, okay, can we switch now? I'm tired. And then your friend will get here, and you'll be you'll be laughing. Anyway, now everyone knows that, so you won't be able to pull that trick on any of your classmates. But this solid rock below is called bedrock. It's this is just what I said. These are soil horizons. You can either call them by their letters, or they have these names: topsoil, subsoil, and regolith. Regolith is where you don't want to be digging. So see these big boulders. You don't want to have to carry them out of this hole. O is this kind of O is basically like the moss and the sticks and like the bugs that are on top, and then A is the light soil that these things are kind of, their small roots are growing into, and then you have that's the nutrient rich topsoil, and then you have B, which is the subsoil, where you can see in this picture there's roots in there, and this is where you'll find clay and less nutrients. So yeah, just kind of O, A, B, C, it's pretty easy to remember. I usually use these words. O is kind of a just means the plants, topsoil, subsoil, and regolith. I just remember regolith is the place I don't want to be digging, topsoil is on the top, and subsoil is below the topsoil. Okay, so hopefully that's clear. If it's not, just send me an email or review these slides. Okay, so two types of soil, transported and residual. Transported soils formed in one place and were transported there to their present location by glaciers. This could be rivers, this could be wind. They're just transported. This is kind of, you can just, it could be glaciers, but it could be other things also. You can tell when the soil does not chemically match the bedrock below it. So say you have this bedrock subsoil, and then you have the topsoil above it, and they're like totally different. Geologists will go out and they really love digging holes, and they'll look at the layers of the holes, and if the topsoil is totally different from the bottom, something happened there. That soil was moved from somewhere, and through the process erosion, which we talked about at the beginning. And like I said, that could be a water action, flooding, rain, wind, any of that. Glaciers are the most epic, but not the only form of transporting soil. And then you have residual soil, located above the rocks that they formed from. In other words, the soil chemically matches the bedrock below it because it's a product of the rocks weathering over time. So this is when you dig a hole and the topsoil matches the bedrock, and you know that just the topsoil is just a more weathered form of the bedrock. So all the weathering has happened at that location. None of the soil has been moved by all these physical weathering forces. They've been weathered chemically and physically, and then the chemical composition matters. So if you had a soil that was really high in iron, and then below it it was just all silicon. Okay, so this is the topsoil and this is the subsoil, or this is the subsoil and this is the bedrock. You'd know that this iron-rich soil was transported. It was moved by something. But if this was also silicon, if it was silicon, then you'd know that this was just smaller particles of this, and that it all happened on that same location. Okay, so this is a kind of confusing graph, but we can work and figure it out. It's basically got all these curves and weird lines. What's this over here? Who knows? But basically the important part is y-axis is annual temperature, so how hot it is during the year, and you have annual rainfall. And this is basically trying to tell us what kind of weathering is happening in each climate. So you've got lots of chemical weathering, you've got lots of mechanical weathering. So let's see, we got strong mechanical, which is like if it rains not so much, but like not super little, and it's really cold, you have really strong mechanical weathering, because like we were talking about before, frost weathering, where the water comes into the rock and freezes, that like devastates rocks. It's really mechanical. It breaks apart rocks. Also, this is where glaciers are, and that's the hugest form of mechanical weathering. So if that helps you, maybe we can answer these questions. What type of weathering occurs in an area that has an average of 165 centimeters of rain each year and an average temperature of 18? So 165, 18. Yeah, you guys are on top of it. Yes, correct. Strong chemical right here. Here we are. 18. Boom. We're like right in strong chemical zone. Yeah, nice job. How about the next one? What type of weathering occurs in an area that has about 140 centimeters of precipitation? This is rain, by the way, if you didn't know. Each year and an average temperature of 5. So, what do we got? Temperature, 5, and rainfall, 140. What we got? Yes, perfect. Moderate chemical with frost action. So, what does this mean exactly? This means that you've got both of these things acting at the same time. You got the frost action, which is what we talked about with the water, which expands when it freezes, breaking apart the rock, and we have this chemical weathering, and that's because we have this. It's warm enough. It's still cold, but it's warm enough, and there's enough water that these chemical reactions can happen that also weather the rock. Okay. So here's where it gets really, really awesome. Transporting of materials. 5 main agents of erosion. Water, glaciers, wind, gravity, and man. So these are 5, but really there's more like 400. But these are the main ones. You can think of all the other ones. But weathering has to happen before erosion. So weathering is the breakdown of large rocks into smaller particles called sediments, and erosion is the movement of those particles or sediments. And just because we're using the word particles doesn't mean that we're talking about really, really small stuff. For example, the glacier will transport boulders the size of a car 100 kilometers in the course of its lifetime, of its movement, and it does this, and I'll explain it in a little bit. But just because we're talking about breaking down, you could talk about breaking down a mountain into gigantic boulders and how those boulders move huge distances. And I don't know if you've ever seen photos of a gigantic boulder the size of a small house in the middle of a field. Where did that boulder come from? How did it get there? It got there by one of these, most likely a glacier or running water. But it's important to think about weathering needs to happen in order for erosion to happen. And these are just some examples. Here we have this kind of Grand Canyon looking river that's split and then kind of eroded these sides here. This is wind erosion. This is really cool because you can tell which part of this rock is softest, which is easiest to break down, and it's this little strip right here, and it's created this huge boulder balanced on this other huge boulder by this very small point, and that's done through probably millions of years by the wind. Okay, so this is kind of a slice cake view of Niagara Falls, which is a really big waterfall in the United States. Isn't it in the United? Yeah, it's it. Not. I'm just talking to myself. So we can see here this diagram, and this basically tells us the different types of material that are supporting this river. Okay, and here's the water coming down, and this is kind of the way that the water moves. It's got this little vortex here, and this is a form of mechanical and chemical weathering, mainly mechanical, physical, and it creates these kind of scoops. The water hits the ground here, it's pushing the water out, and it hits this shale, hits this sandstone, and it erodes these things at different rates because they are different materials. Can anyone tell me which layer appears to be the least resistant? Which is the weakest? Which appears to be the weakest material in this diagram? So we've got dolostone, Okay, so that's a good guess. The weakest rock will be eroded the fastest. So we've got dolostone, shale, limestone, sandstone, some more shale down here. Which has the most kind of scoopy, eroded look to it? I would say it's probably the shale, because this kind of vortex is kind of washing away this shale faster than the limestone, faster than this dolostone. Yeah, shale, exactly. And the strongest is dolostone up here, and it creates this kind of lip. So the shale underneath is being eroded, sandstone is being eroded, and it's creating this kind of cliff right here, but it's also cutting away the cliff, and that's actually how waterfalls form, is that the hard layers on top will be supported by these layers that are kind of eroding faster, and it will just create this lip that stretches out over the rest of this cliff, and it creates this waterfall. And Niagara Falls is really huge. It's kind of touristy and expensive, but there's probably cooler waterfalls around here. But if you ever get a chance to go there, I would do it, because it's pretty huge and amazing. Okay, so this is just kind of getting more detail about products of weathering. You have your soil, solid sediments. These are boulders, cobbles, pebbles, sand, and silt. These are the clay we were talking about, not visible to your eye. So all this means is if you hold some clay in your hand, usually you're not going to be able to look at one particle of clay. It's so small that you can't pick out one particle of it. And that's kind of the definition. When something becomes a clay, you need actually a microscope to see one individual. Like so on the beach you have sand, and you can definitely see one piece of sand, but clay is going to be even more broken down. It's even more weathered than sand. And then you have ions, and these are, you've probably learned about ions in chemistry, but say you have iron, which could be a weathered part of some soil. It's going to have a positive charge, so it's going to be an ion. It's electrically charged. This one just happens to be positive. Some of them are negative, but you have these floating around too. If you have a flood, or if you have a any kind of watershed happening, these kind of ions are leached. They're moved into the water, and it kind of takes these out of the soil, and then puts them in other parts of the soil. So these are the particles. You definitely cannot see these with your eye. You need a powerful microscope to see them. This concept is hopefully pretty easy to understand. This graph makes it look confusing, but all this is saying is that the particles that are the smallest are transported the easiest. So we talked about that earlier. The big particles, boulders, is the biggest up here, solid sediments. Boulders is the biggest, clay is the smallest, and you have everything in between. Boulders, you'd need to have, this graph shows us the velocity of the stream in centimeters per second against particle diameter. So this is just how big the rocks are, and this is how fast the river stream is moving. And you have even a stream that has, whatever this is, 20 centimeters per second. So this is super slow stream. You still can move clay. You can move clay particles with, super slow river. Whoop-de-doo. If you have a super fast river, 800 centimeters per second, you can move boulders. I haven't seen a stream like that. I don't know if one exists, but if you had a huge enough river that was moving at this fast, 800 centimeters per second, and you think about how huge that is, then you could theoretically you could move boulders within it. So the faster the water is moving, the larger particles it can move. Hopefully that's pretty intuitive. But if you have any confusion about that, I bet you could find some YouTube video on if you just YouTube velocity versus particle diameter, you could definitely find something, cartoon or something on that. Okay, so Mount Rushmore, I'm sure most of you have seen this kind of icon before. Oh, okay, so these are all presidents, I guess. The only thing you really need to know is that this is in South Dakota, and it's the only reason anyone ever goes to South Dakota. It basically this is George Washington, this is Abraham Lincoln. These faces have been carved into the stone, and this project took a really long time. And in this picture, you can't really see it, but there's tons of rocks below it, and it kind of just looks like these rocks just fell off and left these faces there. But really, what happened is lots of very hard-working men went up here and carved these faces, and now it's a national monument in the middle of South Dakota. And it won't be there forever. It's eroding. So in 100,000 years, if no one's there to recarve this, it will look like a bunch of blank faces. The noses and things like that this is being exposed to wind, rain, and you can tell that down here, this kind of rock face, this cliff that these faces are carved on, there's rocks falling off. These rocks over here are being weathered, so these rocks are definitely going to be weathered over time. There's going to be, George Washington's nose might fall off, Lincoln's beard. I think if it happens recently, pretty soon, that we'll probably fix it. But anyway, you just need to know that everything is eroding. Nothing is going to be staying there forever. All the mountains that you see, they're changing constantly as a result of weathering, and this is just a example of a certain type of weathering where you're left with a big pile of material at the bottom, and this is called shale. And if anyone's ever tried to hike up shale, then you know how frustrating it is. It's very small rocks that are just they're piled on top of one another, and if you try to step up a hill full of shale, you kind of do one step forward and then you slide back down. And this is kind of a result of weathering. Okay, so why is this important? Basically, it's important because you can tell what has eroded, what has been there in the past by looking at the rock. So different aspects of the rocks that you find can tell you what eroded it. Was it water? Was it a glacier? Was it mechanical? Was it chemical? Was it or physical? Or what was it? And this is another great page with a lot of information on it. I would definitely spend some time taking a look at it. You have running water, glaciers, wind, and gravity, and this tells you pretty much everything. These are characteristics of the sediment. So if they are rounded and smooth, a lot of times at the bottom of a river you'll see these rounded and smooth rocks that are really good for skipping stones. That kind of tells you that, say you came across a dry river and you didn't know that a river was going to be there. You find these rounded and smooth rocks and you say, well, there must have been water here before, because that's what kind of erosion takes place in water. And you can also tell because they're deposited in sorted piles. And we'll talk a little bit about this, but the sorted piles are basically because the water moves different types of rocks at different speeds. So you can have, at one point in the river, one type of rock is there, and at another point in the river, another type of rock is there, and that's because one has been transported more or less easily by the water because of either its composition or the type of river. But anyway, you end up with these sorted piles. So say you're walking in the desert and you find this huge area of rounded and smooth rocks, but there's no water in sight. You could actually be walking on a place where there was a river thousands of years ago, and the reason that geology is so cool is because if you didn't know that, you would just walk right over this area and not ever know. But because you're all going to become geologists, you know that if I see rounded and smooth rocks everywhere and sorted piles, I'm stepping on what used to be a river, which is pretty cool. Similarly, glaciers, which are just totally ridiculous. Some countries are shaped mainly by glaciers, and one great example of that is Iceland, where everywhere you go you can see evidence of glaciers. And if you don't know what a glacier is, basically it's when water on a mountain turns to ice, and the ice begins to accumulate and grow on the mountain, and then it's propelled down the mountain by its own weight. And as this gigantic, massive thing that keeps growing moves down the mountain, it carves these grooves in the mountain, and it picks up boulders, and it scratches the mountain, and it can move these gigantic things, and it just keeps growing and growing and growing. And then as the climate gets warmer, then the ice starts melting, and it begins to have these huge chunks of ice that fall off of it. And then when it's all melted, you're left with all the rocks that were transported by the glacier, and that's how you have these gigantic boulders in the middle of nowhere. And it's because they were most likely transported by glaciers. You can tell what the sediment looks like because it's kind of jagged, and it's not smooth like in running water, because these things are being broken apart, smashed by the ice, and picked up and put down, smashed into other rocks. They're being completely obliterated, and they're completely unsorted. They're just mixed up in a big pile of glacier nonsense, and then it just melts, and they just kind of drop down. So that's pretty self-explanatory. They're scratched, they're grooved. This is because of, like I said, these sediments are really taking a beating inside the glacier. And here we go. Boulders can only be transported by glaciers. We saw a example of a wind-eroded rock earlier. It's basically generally the wind erosion. Oh, I froze. There we go. Generally, the wind erosion is because you have little particles in the wind that are being propelled towards the rock and hitting it, and just that small impact creates a very, very small erosion. And when you multiply that by millions of particles and millions of years over time, you get these kind of weathered, eroded rock faces. And if any of you ever go to Utah in the United States, there's tons of wind erosion that happens there because the main rock is called sandstone, and the sand is in the air also, and the wind propels the sand, and it hits the other sandstone and creates these pitted random holes and frosted glazed look. They're in sorted piles as well because, again, the wind can move smaller particles further than larger particles. And in general, we're only talking about very small particles, because if you think about it, you can't transport a boulder or even a small rock with the wind generally, unless you're talking about a storm of some kind. But usually wind is only going to be propelling small particles. Gravity, sediments that are transported by gravity are found in piles at the bottoms of cliffs or steep slopes. They appear angular and unsorted. So this is just like if something's falling off of something else. If you have a hill and things are kind of tumbling down this hill over time, then that's gravity that's working for you. So yeah, like I was talking about, wind erosion is only really small particles generally, unless you have what's called extreme wind erosion. And that's kind of, if anyone's seen the movie The Mummy, or seen any crazy dust storms. I believe there's one in the movie Stargate also. But yeah, basically these gigantic clouds of sand and stuff, they can come in and really destroy lots of stuff, because again, these are tiny particles with tiny impacts, but you multiply that by billions of little particles traveling at high speeds, and you can get a lot of erosion going on. This is just an example of where a glacier scraped across the bottom. This is what you get, these little striations, which is these lines that happen here. So yeah, running water can transport sediment in 3 ways. So now we're talking about rivers, or streams, or whatever you want to call them, cricks, whatever. But you have solution, which would be like ions or clay particles. They're dissolved in the water. This is kind of what you can't really even see generally. And then you have suspension, which is most of the clay, and this is what makes rivers look either really clear if they have very little suspended particles, or very cloudy. So you have the Chao Phraya River. It's got a lot of suspended particles. It's really cloudy. You can't see the bottom. It's because there's tons of suspension. So you have a high level of suspension is what you'd say. They're neither at the bottom or the top. They're usually suspended in the middle. And you have saltation, which is when you have these kind of medium-sized rocks, depending on the river, on how fast it's going. You have medium to small rocks kind of bouncing along the bottom of the rocks. They're still being moved and transported, but they're kind of just, their weight keeps them on the bottom, so they're always on the bottom, and they're moving much more slowly than items in solution or suspended in suspension. So this is just a little bit of vocabulary. Basically, if you are really trying to talk about what happens during erosion and you want to use the right terms, these are just a few of the terms that you can use. The riverbed, you've probably heard this, that's just the bottom of a river. The bed load is those saltation pebbles and rocks that are bouncing along the bottom. If you were to try to describe all of those, say that this stream has a bed load of this many kilograms per mile, so you'd say that'd be considered the bed load, and that's different for each stream or river based on how fast the river is moving. And we saw that earlier in a graph. You can go back and reference that after the lecture, but it's basically with a larger stream, you get larger rocks going across, so we'd have a higher bed load. And if you had a very small stream, you'd have very small amount of rocks and pebbles moving along, small bed load. Downcutting is when weathering and erosion along with running water cause the stream or river to become wider and deeper over time. So this is basically, you have let's see. This is kind of, this is your river segment, and you have forces. The saltation, sediments rolling along the bottom, can actually erode the river so that it becomes deeper over time. And the same thing happens if you have kind of a winding river. Okay, the river is moving this way, and you have these rocks and things that are in suspension kind of grinding away at this river, so then it becomes even more drastic. So this is downcutting. Weathering and erosion causes stream to become wider and deeper. So old streams are going to be generally wider and deeper than young streams. This also depends on what the material around the river is made of, but generally you can say a gigantic river that's really, really deep is going to be older than a small stream. I'm going to skip this slide because we can come back to it if you want, but this is basically just showing how rivers can drain off of mountains, but these are all different perspectives and it can be confusing. So what affects the rate of erosion? What do we know already about rate of erosion? So we know that it is affected by heat and rainfall, right? We know that about chemical. We actually saw that graph that was kind of had all the curves in it and stuff. But this is a different way of putting it. We have the slope, the gradient of the land. So this is basically like if you have a really steep slope, then you're going to have more erosion rate. You're going to have a higher rate of erosion. It's going to be eroding faster and faster and faster, because as this erodes, it's going to become more steep, and then this will be faster. So it's kind of an exponential rate of increased erosion. You don't really need to know that, but just know that as the slope increases of this line, the water velocity increases. So the water is going to be moving faster on a steeper slope, and the particles that can be carried by the faster water are going to be larger. So as this slope gets steeper, the water moves faster, larger boulders and rocks are being washed down, and the amount of erosion increases. The size of the water or glacier, so the bigger river and the bigger glacier, obviously you're going to have more erosion. Position within the running water. So this just means that water is traveling faster around the outsides of the turns. So this is we're going to talk about this in a second. Basically, I'll just go to the next one because this picture isn't loading. Okay, so I don't know why this picture isn't. There was a photo here, but it's not working for some reason. Maybe that doesn't really matter. Okay, so don't think about the Oxbow Lake thing yet, but basically what we're talking about over here, position within the running water. So this is a really great diagram. As the water flows down this river, so you can think about this, if any of you have raced cars, or you should be able to get the PowerPoint. I don't know if you can't get it. Okay, yeah, they'll be posted later, so you can review this if you want. But yeah, say you have this curve. The water is moving faster on the outside than it is on the inside. So anyone who's raced cars, yes, I will give you the link to the. He says he wants the link to the PowerPoints. He can't get it. Okay, so yeah, it'll be on the website. You can find it whenever it's posted. It should be pretty soon. So yeah, again, so if anyone's raced cars or go-karts or gone around a turn, you know that you go slower. It's faster, time-wise, to go, around the inside of the corner. If you go around the outside, you're going to need to go faster to maintain the same speed, to maintain the same distance. So you're going to need to increase your speed to maintain the same distance. So that means that as the faster water, so what we know about erosion is that as the water is moving faster, which it is on the outside of the curve, it can transport larger particles. So this side is being eroded more. As the water slows down on the inside, it can't support some of the same particles, so they drop down to the bottom. So this side is increasing and this side is decreasing, and what you get is this pattern here. So what used to look like this, the river is going to deposit sediments because it's slowing down on the inside and it's speeding up on the outside. So it's going to take particles from this and it's going to leave particles here, and then you get something like this, and then eventually the river, its most efficient route is just to go straight, and then it's depositing on these curves and on this curve, it's depositing, and then they grow together, and it actually forms a C-shaped lake, and this is called an oxbow lake. So the stream starts out like this, and then it gets like this, and then it gets just crazy stream-like that, and then eventually you get these little cutoffs. The stream will kind of cut this off and leave it here, and that's kind of what's shown right here. Okay, so what's happening here? What kind of erosion are we seeing, and what's acting on this kind of watershed right here? So this is just like the Niagara Falls diagram, right? This is the physical weathering we were talking about, where the harder sediments are on top and the softer sediments are on the bottom, and it kind of creates this vortex, and the lip comes over, and so you get this series of waterfalls here. And this is probably because this is hard. This is much harder, dense material. Dolomite, I believe, is what we were talking about before. This is an example of, eventually the meandering river is going to happen, and then this is an example of a floodplain where this kind of valley is carved out. And I'm actually out of time. We can finish this lecture a different time, but yeah, if you have any questions, please send me an email or review the slides. There's a lot more, but we'll cover it, and we'll revisit some of these ideas as well. Okay, bye.